Hello everyone, welcome to GATE Pass. I am Dr. Poonam Nigam, and in this video we are going to take two more problems, and that will finish our thermodynamics problem of 2021. So the first problem which we are going to take is question number 21, which appeared in GATE 2021. Okay, so today we are going to take only 2021 problems. Fine. So in this case, van der Waals equation was given in terms of your reduced pressure and temperature and reduced molar volume, and they have given you the value of compressibility factor at critical point, that is equal to 3 by 8. Reduced molar volume and reduced temperature are also given. Okay, and they have asked you to find the value of compressibility factor. Okay, so this was the question. Let's quickly first brush up our concepts to solve this problem. Okay, so we all know that your ideal gas equation is PV is equal to RT. Okay, now where V is your molar volume, that's why I am getting rid of the N, which is number of moles over here. Okay, now this equation, it applies for ideal gas, but if I want to write an equation for a real gas, then what I do is I write it something like PV is equal to ZRT, where Z is my compressibility factor, and it gives you the deviation from ideal behavior. Okay, so I can rearrange this equation and write PV by RT, that is equal to Z. Okay, now let's first see how reduced properties are defined. So when I am saying reduced pressure, what I mean is that it is equal to pressure at some point divided by the critical pressure. Okay. Similarly, my TR is defined as temperature at the same point divided by the temperature at the critical point. Okay. Now, what are critical pressure and critical temperature? Critical temperature is that temperature above which you cannot liquefy a gas. Okay, and your critical pressure is the minimum pressure which is required in order to liquefy the gas which is present at critical temperature. Okay, so this is how critical temperature and critical pressure are defined. So basically you have, this is reduced pressure, reduced temperature. Similarly, I can also define my reduced molar volume as the molar volume divided by the molar volume at critical point. Okay, so these are the definitions. Now let's say I have written this equation at some point, okay, where my compressibility factor is Z. Now I can equally well write this at critical point as well. So then my equation will be PC VC upon RTC. Let's do one thing. Let's divide this equation by this equation. Okay. In that case, what will happen? P will get divided by PC, V will get divided by VC, R will get cancelled, and T will get divided by TC. So what I get is basically Z divided by ZC, that becomes equal to PR VR upon TR. Okay, do yourself and check that you get the same equation. Now, so my compressibility factor will be equal to ZC PR VR upon TR. Okay, that is what you have to find, your compressibility factor. ZC is given. Now PR is given in terms of TR and VR. Okay, so I am going to replace this over here. So I am keeping ZC VR by TR, and I am going to replace my PR with this van der Waals equation which is given over here. So I will write 8 TR upon 3 VR minus 1 minus 3 upon VR square. Okay. Now in this equation you know everything because VR and TR are given and ZC is given. So put everything in this equation, simplify, and the answer which you will get is basically 27 by 32, or the answer which is given in the key is 0.843. It's a very simple question. Okay. Do this mathematical manipulation on your own and you will get this answer. Okay, a brief discussion on the value of compressibility factor. Let's talk about the values of your Z. So you all know that for ideal gas the value of z is equal to 1. That's why your equation gets reduced to this form. So for ideal gas, you have z which is equal to 1. When you have real gases, then your for moderate pressures, okay, for moderate pressure, the value of z is less than 1. That is what we got in this question, okay. Why it happens? Because when the pressure is increased, the molecules come close to each other and then they experience some intermolecular forces, okay, and then the volume decreases. So that's why your z comes out to be less than 1, okay. Now for high pressures which are very close to your critical point, in that case what happens is z becomes greater than 1. It happens because when the molecules come very close to each other, then they kind of repel each other, okay. In that case your z becomes higher than 1, okay. So this is a brief description. Now z can never be equal to 0 or it can never have a negative value. Keep this in mind. Fine. So now we will move on to the second question. So the second question which I am going to take is question number 23 from GATE 2021 paper. In this, the value Cp by R is given as a function of temperature and the value of R is given, and you have been asked to find the rate of change of molar entropy with respect to temperature at constant pressure, and you are asked to evaluate this quantity at a temperature of 1000 Kelvin. So let's first write down what does this mean. What you have to evaluate? You have to evaluate ds by dt, rate of change of molar entropy with respect to temperature at constant pressure, and T equal to 1000 Kelvin. Okay. So if you remember the equation of how to calculate the change in entropy for an ideal gas, okay, then you can directly use that equation. I am going to derive that equation for you. So let's start with the equation H is equal to U plus PV. Okay. Take the differential, and the differential is dH is equal to du plus d of PV, or I can write dH is equal to dq reversible minus PdV, open this, plus PdV plus VdP. This cancels and you have dH. Now dH for ideal gas we have seen in previous video, one of the previous videos, that dH is, you can write as Cp dt for a, okay, for ideal gas this relation is applicable when you are undergoing a process which is a constant pressure process. So dH is equal to Cp dt, that is equal to dq reversible plus VdP, okay. Now we have been asked to keep pressure constant, so I can forget about this term, okay. Now let's divide by T. Now what is dq reversible by T? That is nothing but your ds, that is equal to Cp by T dt. Because you have been asked to evaluate that integral, let's take a differential with respect to T, so I get this Cp by T, okay. This is at constant pressure, that's what we are evaluating. Now you have been given Cp by R value, so what I will do is, okay, so I will just take R over here, multiply this, so that I get what is my value of Cp, R times this function, okay. So I have R times 2.46, let me write it a little above, okay, so that you can see clearly. So I am going to write ds by dt at constant P, that is equal to Cp by T, that is equal to Cp is nothing but R multiplied by this and divided by T, so R by T, and I am just copying it, okay, 45.4 into 10 raised to minus 3t minus 14.1 into 10 raised to minus 6 t square, okay. If I take t inside the bracket, okay, let's take t inside the bracket, this thing gets divided by t, t and t gets cancelled from here, and this thing 1t gets cancelled, so you have this value, okay. Now let's put the values 8.314 and T is 1000. So if I take it in the numerator, it becomes 2.46 into 10 raised to minus 3 plus 45.4 into 10 raised to minus 3 minus 14.1 into 10 raised to minus 3. Okay. So everything is in is multiplied by 10 raised to minus 3, which I can take out and add everything else, whatever this is there. If you add it and then multiply, it comes out to be 33.76. Do the multiplication and your answer comes out to be 0.280. That is the answer. Okay. So your rate of change of molar entropy with respect to temperature at pressure, constant pressure, and T equal to 1000 Kelvin, that is equal to 0.280. This is the answer. Okay. And of course the units will be the same as that of R, that is joules per mole per Kelvin. So if you know the equations, or even if you don't remember the equation, you can derive it in hardly 1 minute and solve this question. So I hope you understood, and if you like my video, please don't forget to subscribe and like, and thanks for watching.